Okay, well, gotta turn on the mic. Okay, can you hear me all in the audience? Great. So, thank you all, and thank you, Vin, for that nice introduction. I'm happy to be here with you and to celebrate this centennial of the birth of the modern programmable computer. Not that there was nothing that came before. I actually had the experience of actually trying to crank the Babbage analytical engine in the British Science Museum, to the chagrin of the curator of the museum, who rapidly came across with a chamois cloth to wipe all of the possible oil, sweat, whatever you get on it. But modern computing really does trace its roots to the work that Turing did, some of the early computational devices. Those of you who followed that field know that the most of the early machines that get referenced were actually special purpose machines. And what Turing came up with was a Gedanken model of a general purpose computing engine. The first programmable one that I had known about was started here in Princeton. There was a parallel one, as we all know, in England, and I think those two were essentially on parallel tracks to demonstrate that concept. So what I would like to do today is really focus on just a few basic ideas in terms of building real systems. I mean, everyone who has grown up in the mathematics field knows that there's a difference between a proof and a beautiful proof. Not that you could ever write it down, but it has to do with simplicity, elegance. It has to do with sort of the compactness of the rationale and the logic that goes into it. There's a certain beauty in a really gorgeous proof like that. I think there is a similar kind of thing in systems that get built in the real world. You can build things that do a function, but they don't have the largesse of symmetry or elegance in the same way. So I'm going to try and explain what that is from my perspective and see if I can put it on a platform that makes it come alive for you as well. So I want to start with, let's just see, I guess this will do it. Let me start with the notion of abstraction. Some of these terms will show up in mathematics, they'll show up in computer science, they'll show up in programming languages in different fields. But to me, abstraction is a way of describing something that lets you kind of get to the essence of it without saying anything about how you actually do it. So, for those of you who follow things, the internet has been around now for about 40 years, and for a technological contribution, that's actually a very long time. And I'm going to come back and ask if anybody knows exactly what the essence of the internet is. But for the moment, let me just say there's something about it that's caused it to last for a long period of time. And if I had to do it by analogy, I would pick a few other examples. Radio broadcasting has been around now for roughly a century, to first order. And during that time, everything about radio broadcasting has changed somewhat. We've gone from AM to FM, these antennas, those antennas, different receivers, now digital, and yet the notion of radio broadcasting persists because it's a description of the capability at a high level of granularity. Very abstract notion of what it is. It's less defined perhaps than the internet. But I was going to give you one more example, and this is something that's not meant as a trick question, but can I just see a show of hands in the audience of how many people know what a book is? A book. Okay, everybody knows what a book is. So let me tell you why I asked that question. I'm not trying to say that people haven't used books in their lives, but if you go into a bookstore and buy 10 copies of any book that you're interested in, they all have the same ISBN number. And the reason is they're all the same book. Now that may seem like a strange way to describe it, but the book is not the paper and the ink. The book is actually the way the information is structured. So the book really talks about the information structure. And that's going to be a key ingredient when I talk about how you think about managing information in the future. I'm going to focus more on the structure of the information than how it's actually stored or how it's actually presented or manipulated and the like. These are very fundamental notions. There's also a more abstract notion of what a book is, and that's where the copyright industry comes in. My wife is in the audience, and she's a copyright lawyer, so I've been trained very well. But the essence of copyright is in this notion of a work, which is this non-specific notion. I mean, it's the story, but you can't get it copyrighted until you actually reduce it to actual words and sentences. You have to structure the notion, which you could probably describe to somebody. It's a love story, boy meets girl, and so forth. But to actually make it into a structured work, you've got to turn it into words and sentences and so forth. So here are some examples in other fields that were major advances in their time. In the field of mathematics, you all know that we moved from fixed notions to variable notions, in the early 1600s perhaps, when the notion of variables were introduced. If you wanted to track a formula like y equals x squared, they had tables. So when x is this, y is that, and you had all the tables, and the idea that you could represent that as an abstract notion with variables was very difficult for people to accept at the time, so I read, not having been there, but apparently the idea that you could actually prove things about all of these different relationships were in piles and piles of paper by manipulating this simple expression seemed pretty far-fetched. In the computational world, we have a similar kind of thing, and there's probably a pointer here, so let me see if that'll work, or that'll work. Here we go. So if you have a notion of y equals x times x, which is just a different way of writing that, I could have written it as x star x, I suppose, or any other form, but let's assume this one will stand the test of time. You can imagine that can be mapped into very many different ways of actually doing that computation. So this is the abstract description, and this is a very realized form of it, different programs, different programming languages, different machinery perhaps, and the like. So it's compiled into a real world implementation. And likewise, you have another notion of abstraction as you move in environmental worlds from internal notions of what systems can deal with and they know to external versions. So if I'm on a system, oh, this somehow, as it got shown on this version, should have been here. So if you can mentally make that on my slide, it looks just like that. But, so if I'm in one internal system and Bob is well known to me, you can send email to Bob and it may know who to.
Just make this full screen for you. Sorry about that.
Okay.
I'm sorry. Jeez. This mouse doesn't want to work.
Probably right down here. You
I got it.
Okay. Still didn't do it. Okay. Too bad. So, but if I move outside into a larger world, let's say it's a closed net like the ARPANET was in its early days, Bob is not a distinguishing characteristic. So I need something that will tell me exactly what I'm talking about in that constrained world. And if I went out into a larger world like the internet, for which the ARPANET would be one component network, then I might want to say something like Bob at CNRI.us, which would distinguish it from a very specific one in the ARPANET. So these are three examples of where abstraction is really important, and you have to distinguish between the abstraction and the implementation of that abstraction. So I mentioned I was going to ask about the internet. So which of the following do you believe is accurate? And it could be none of the above, all of the above, or even some of the above, I suppose. I should have given. Question number one, the internet a network? Is it a global information system? Is it a generic logical abstraction in some ways? Is it none of the above, all of the above, or could it even be some of the above? So I'd like to just see a show of hands in the audience again. How many people think the internet is a network? 1, 2, 3. Okay, I would say about a third of the people in the audience. How many think it's a global information system? So the same people, some of whom who raised their hands before are raising it again, so it looked like about 40%. How many think it's just a logical abstraction? All right. How many think it's none of the above? Oh, we got at least one person. How about all of the above? Wow. Well, let me just say that here is a fact, that the internet's now been around for 40 years, and the reason it's been around for 40 years, because in my view, it is actually not a network. It involves a lot of networks. They handle transport of the data, the packets, but in fact, the network itself is replaceable. So none of the networks that were in the original network are around anymore. We've had lots of new ones, and we'll have lots of new ones in the future. But in some sense, by describing the internet at this very high level, we allow for any kind of network technology in principle that may show up now or in the future. Because all it does is it describes the means by which it can make them all work together. Now, that was a fairly narrow definition when we started it, and no level of abstraction is ever guaranteed to be universal forever, because you'll see new things you want to do. You know, as we heard from Andy Yao, there may want to be a quantum version of some of this communication, and who knows what that will do if it really becomes real. But that was one of the points I wanted to make, because I'm going to come back to this issue as we go along. So let me talk about the same thing in terms of computation. What would be a notion of a generic computer? Well, you might say what Turing came up with was a generic computer, in that it will do any kind of computation. In fact, the whole notion of computable functions really derives from the notion that you can actually run a computation and presumably get an answer. But if you have a computer and any program can be run on it, and I'm presuming here we mean a program that will actually produce an answer rather than go into an infinite loop or just not converge. Well, what if the machinery could be reconfigured without a parts replacement? That is, you could say to this machine, you're running this way now, but I want you to change and be a different kind of machine, because my computation depends upon a whole series of different underlying machines. Now, the purists will probably tell you it doesn't really matter whether it's in this form or that form. If it was, you know, a machine that could do computing, you could do it one way or another, just like, you know, if you can do something in binary, you can probably do it in other forms as well. It just may be a little more difficult. Well, what if whatever you're doing, you had to live with fixed attributes? Would that make it generic? So if the memory couldn't be larger than a given size, or you had a certain amount of chip real estate that you could make use of, or certain technology that could be used to process it, maybe you could even process it in real time. So maybe even some of the physical parts could be replaced automatically. Do any of these have to be there for a machine like this to be generic? And if you had such a reconfigurable computer, in what sense, if any, would it allow for new computational methods? So if quantum computing really did come along and a conventional machine can't do it, but you had another kind of machine which could reconfigure itself to somehow do quantum computation, would that now be a generic machine? What else might come along later that would need to be dealt with? So we don't know. So now I want to ask the question about the internet itself. So what's generic about it? So in one sense, and here's a path that this is, let's say, some application program or user, and this is another one he's using. This would be sort of viewed as an end-to-end kind of function where this user is trying to deal with this function, and the networks are all in between, and that user just sees the networks as just passing the bits. Okay, but then there are these things called routers. We called them gateways when we started, and these routers help you figure out where to put things, where to send things. So you can imagine that you could view this as going through the routers to get here, or if you want to be more precise, you could view it as going to a router, down to a network, up to a router, and then kind of wiggling until it finally gets there. But the reality is, every one of these things down here can and will disappear in time. In fact, virtually every one that existed historically, except for perhaps the Ethernets, have long since gone. And guess what? Even the routers will go. So what is constant about the internet are the protocols and procedures that define how the information moves and how these things get stitched together. Exactly how to say that in a more generic way, I don't have a y equals x squared simple version of that, but you can actually describe the protocols, how they work, and anybody who has lived in the computer language field would probably understand what it means to take those protocols and describe it in a more formal sense. But you can also say, here's an implementation in this world, in that world, and so forth. So now I want to talk about, if this is really generic, what about adding capabilities? This is a subject of great interest externally, because there are some people who believe the internet is really just an end-to-end thing, and this is all about packet transport. I happen to be of the opinion that there is no system that stays stagnant and lasts for a very long time. It always needs to grow and evolve, and the only way to grow and evolve a really large worldwide system is by virtue of adding new capability and integrating it with the old. So for those people who think that layering is the only answer, I would just simply say, look at the clothing that you wear on yourselves. That is layered on you as an individual, for every one of you. On the other hand, your circulatory system is not layered on your gastrointestinal system to get sort of personal and internal. These are just capabilities that are all integrated together to form a whole. So what if you had the ability to add more capability here? See, these little red squares, you could think of them as sort of more applications of some sort, but I've shown, here's one that's sort of available that you could make use of somewhere. Here's another one that's maybe either partially or totally embedded in this network. These are networks down here, remember? And here's another one that may be partially or totally embedded in a router. Now, why has this not been embraced that much, globally? Well, one of the reasons is that if you allow for these kind of capabilities to be added, then what expectations should a user have about what's going to happen? More importantly, as you'll see in my upcoming slides, is who actually gets to decide about that. So if this were a capability inside of a network and that network provider decided to do something rather dastardly, you might find you have unexpected results. We had a very serious case of this when one of the providers who was dealing with naming in the internet basically said, well, why don't we just help out people who type the wrong thing by figuring out what they really meant, and we'll connect them to that site. And it was a huge battle that finally went into the courts. The thing was decided in favor of not doing for the user what the user didn't choose to do for themselves. So you at least know what to expect. However, if you really think about how this might work, if you actually view this as the model, which is one end-to-end model, but you allowed for something called handoff and reconfiguration, there's no reason why, having now communicated with this end site, that end site couldn't say, oh, I see what they're trying to do, let me hand it off to another end site, and now the user is going to get a series of results that's determined by what this site determined, sent somewhere else, and eventually they get something back. Hopefully it's what they wanted. Well, this is a start into a topic that we, myself and one of my colleagues, started to explore back a number of years ago, and that is, what would the role of mobile programs be within the internet environment? Here's a case where you might say something, we go through a net, I've left the routers out just for simplicity, and it ends up at this intermediate application. Well, if it's a mobile program that got generated, this application might explore it and say, whoops, I think I better send it to this one because I need some more information. I'm trying to figure out the price of tea in China, so I need to figure out what the Chinese tea is, and it's in this price, but then I need to figure out how much is the Chinese currency worth today in dollars, because I wanted the answer in that form. And there may be other intermediate steps that have to go along to convert it, and so these are all happening. Now, is this an end-to-end kind of capability the way people tend to think of it? I say no. And what's more important is that if you had this kind of capability for the first time, it allows a user to break away from something that we have handcuffed them to ever since the beginning of computer networking. Namely, if you want to do something on the net, what you have to do is manipulate a keyboard to make it happen in real time, and you've got to stay hooked up while it tends to go on. Now, there are a few examples where people have tried to break away from that, to be sure, but there's no general purpose method where you go up to the machine and say, I want you to go find this information or do this thing, and I'll come back in a half an hour and hope to see the result there, where The result was gathered by going to many different sites on the net, pulling information, putting it together, and bringing it back in one piece. So I think this is a model for the future. It's not an end-to-end model, to be sure, but there are a lot of people who are very scared and concerned about this because they're afraid that their model of what should be happening isn't what's actually going to happen. So I'll come back to that as well. Now, within your own computer, I guess the colors don't come out here either, but this was a different color. If you have a typical traverse from an application out to some external world, let's say a network, you're going to go through a number of intermediate steps. So, for example, let's assume that it's information coming in. There's a driver that's handling the interface, both hardware and software. This is the software piece. You might do some IP-related stuff, make sure it's the right place, and so forth. Maybe some TCP-related stuff, whether it's error checking or putting things back together again or whatever. Maybe some pre-application stuff, which has to do with how you package it up for that application, how you put it on the screen, and so forth. And then the actual application itself. But this doesn't go like that anyway. What happens is somehow it's going to constantly dip up and down into the operating system, which those programs rely on to do certain functions for them. So we already see it here, and most of us have no idea what the operating system is actually doing, nor did we ever get a real specification for it. But somehow we've managed to live in this environment, and my guess is it's more like what the future is going to be in the networking world than anything else. It's not a straight pipeline. Furthermore, an end application may very well want to reach across and do something in the driver, prompt something, say, put this out first, or when this comes up, let me know immediately, rather than allowing it to propagate, because something down here might stack it up. If it's voice, for example, it might get stored until you got the previous voice packets coming in, whereas in fact, we know if you wait more than a little bit of time for voice, you might as well throw it away because it's too late to play out into a continuous stream. So let me talk about what some of the attributes are of information that really wants to be dealt with in this larger environment. And I'm thinking of breaking from the mold of imagining everything within your purview to a world where somebody else is trying to access information that they didn't create. It's got references to things that they didn't know about or don't know about. And more importantly, it may be information that you're trying to access many years in the future. These could be national archives of one sort or another. The university might decide it wants to take all of its serious information and make it available to future generations. So it might be centuries later that somebody's coming back and trying to understand what this information is all about. So some of the attributes that I think are relevant here, one, I'm assuming it's going to be in digital form. That is, whatever we do with our paper records, I'm not talking about today. Although you can digitize paper records, as you well know. Except if they're very old, in which case you may have a lot of loss, as we've seen with things like the Dead Sea Scrolls and various parchments and the like. We're assuming it can be created anywhere in this digital world, digital network world. It can be stored anywhere in the internet. Might have been created many years ago. It may have formats and conventions of the creator's choice. You may know of some of them, you may not, but I would just simply ask if anybody in this audience, does anybody know what VisiCalc was? Or anybody old enough? Yeah, okay. So if somebody sent you a VisiCalc spreadsheet today, would you have any clue how to manifest what's in there? Probably not. Some might. In 1,000 years, I guarantee you, nobody will know how to do that. But it doesn't mean that it can't be done. So what you need is some help to do that, and I think the help can be built into the abstractions that we deal with. So I want to talk about that a little more. And if it really has come from the distant past, you have to realize that much of even the semantics may not make sense anymore. Words that made sense may have different meanings today. Names that existed back then may not be around anymore, and so you've really got to separate out the linguistic, ontological kinds of issues from those that have to do with either the manipulation of the bits or accessing the bits and so forth. So much of what I'm going to say in the remainder of the talk really if you look at it carefully enough, has origins in prior work in different fields. So mathematics has contributed some, and we've heard some of that in these talks. Programming language field has contributed many of the ideas in very different constructs, database systems, networking, and so forth. And when you think about it, just to give you one model, things that are considered a feature in one particular use may turn out to be exactly the inverse of what you want to do in another context. So I'll give you an example. We lived through the invention of and the dissemination of object-oriented programming languages. They're still in widespread use today and probably will be for a long time. One of the real advantages of it was to save the programmer all the trouble of having to deal with the data structures and the like, so you could have these objects that you could deal with specified methods and sort of be done with it. If you are in the intellectual property business, those data structures are your crown jewels. So you never want to see them put into arbitrary structures by others, because every use that one makes of those internal data structures, if I can call them that, is probably going to be the subject of licensing by some IP lawyer. And it's revenues that might come into that company. So you have a very different notion of what kind of model you're dealing with when you are trying to live in a world where the actual data structures themselves have value. And increasingly we're seeing data structures with a lot of value, whether it doesn't have to be, strictly in the copyright related fields. It can be in many other fields as well. And it may, in fact, be informational stuff that's pure numbers, like financial information, where you want to control who can see what about it, who can do what about it, or medical records where you want the same kind of control. So those are some of the attributes I think are really the most important. So let me now talk about some of the primitives that you might use to deal with these attributes. Well, one way I think about this field is in terms of a thing I call digital objects. In the case of all the networking that we did, we moved from bit serial transmissions, which were the de rigueur in the data communications field for digital data, to basically packets, whether they were cells in ATM or frames in frame relay or packets in the ARPANET or the internet. These were just simply addressed chunks of data, the goal of which was just to get them to some other place. Nothing more. It was just mainly connectivity and worldwide communications. So in the case of a digital object, this is slightly more, a slightly higher level of abstraction. In general, in moving packets around, you have no idea what's in them. But a digital object is presumably a known commodity. It may be encrypted so you can't see it, but it's basically structured data that's got a unique persistent identifier. And furthermore, these identifiers are all resolvable. That's a requirement for it to be a digital object. So if you want to put this in perspective, if you were using your own computer, you have files that you store on your machine, it's on your hard drive, you probably, or flash memory, you probably don't know where they're actually located, but there's an internal mapping thing that will take some kind of a name that you created and controlled, which is unique on your system, and it will map it into the right place so you can bring that back and understand it. It's also formatted and structured. So you can think of a digital object being like that, except it's no longer tied to a machine. It isn't even tied to a time frame. So if you're in the publishing business, or you're essentially trying to make information available over the long haul, you would really like to be able to get to that structured data without having to go through all kinds of intermediate steps that are difficult, or worse yet, to go search for these objects. You'd like it to be all made easy for you. So I'm going to get into that. So the next part that really becomes critical is the notion of types and type resolution. Now, typing came out in the computer programming language for sure. Type value pairs or name value pairs have been known in the database world for a very long time. But if we're talking about a large system environment and millennia perhaps, then you can't make the assumption that just because somebody 1,000 years ago knew what a type meant, that somebody 1,000 years later is going to have any clue. So each one of these types, we assume, are also unique persistent identifiers that can be resolved to information about what that type is. And every digital object is structured in terms of type value pairs, and there could be multiple of them, call them elements, that can be then understood in principle by any machine that receives this kind of structured thing. Now, whether you can actually manifest the data, that's a very different issue, and I will come back to that one. But these are two critical things. Now, the types can be resolved into different languages. They can tell you the programs that need to be used to manifest the data, and so forth. This is a particularly important one, and one that I think is going to come back to bite us, because almost every major system that I know of that's being created comes with very specific interfaces. Even the TCP/IP protocols are a kind of specific interface, so that you can't arbitrarily change it. And look at how much difficulty we've had in going from IPv4 to IPv6 addresses. It's been, what, 16 or so years and counting, and we are still finding resistance in many parts of the world to that small, I call it a parameter change, but you understand the point here. So the interfaces that we have really need to be scalable, and by that I mean to be able to handle arbitrarily large numbers of systems. They need to be extensible, that you can add new functionality, and they need to be very broadly applicable, so it's not constrained by the type of application that you're trying to make. And I'm going to come back to that too. I think the key to it is to make those interfaces be based on the use of identifiers. So these are essentially typed interfaces. Now, metadata is going to be one of the primitives we care about, because if everything's got an identifier, and if identifiers are key to actually accessing the information, you're not going to want to remember the identifiers. So you're going to need metadata registries, which help you search for things. And the important thing is it will allow you to deal with your own private information. So you don't have to worry about putting it in a public forum for some public search engine to go find. This could be your own business data, it can be your personal data, it could be your financial data, anything that's considered personal. You can put in these registries, and if they're constructed properly, they'll have enough security to make sure that only you or selected parties that you identify can actually access it. This security really needs to be built in right from the get-go. If there's one thing we've learned about, it's hard to add security after the fact and do a good job of it. So let me talk about addressing now. This gets to this notion of generality. In the ARPANET, the way we addressed computers was by wire number. So you wanted to send something to the computer at UCLA, which was number 1, you addressed it to essentially wire number 1 on node number 1. 1,000 years from now, nobody's going to know what wire number 1 on the ARPANET meant. So that's an addressing mechanism that was tied to that technology at that point in time. Well, when we had a few more networks to deal with, the satellite nets, the radio nets, the ARPANET, that wire generally didn't have to go to another computer. It could have gone to another network. So we didn't want to have people then figure out how to tell that other network what to do with what came in, because you'd have to then understand what wires were on that network and go to that level of description. So we invented the notion of IP addresses so that you could give a unique one to every machine, and then that net would understand by interpreting it what was supposed to happen. And that's, in fact, the way all of the transport in the internet actually works today. It's off of these IP addresses. The DNS is a naming system that lets you map more convenient names into these IP addresses for purposes of transport, but many applications still make use of them. The web really simplified what the ARPANET could have done many years ago in terms of file transfer, but these were procedural activities. You actually had to manipulate on the keyboard what to actually do, and they proceeded by virtue of appending the domain name of the machine with the file, made it possible for a procedure out in the back to do all the things you had to learn to do yourself on the keyboard. And also handling the graphic presentation of results, so you could deal with different screens and the like. So if we're talking about the digital bookshelf, we have a couple of problems here. Problem number 1 is that these references in the back, let's say, of a digital book need to stand the test of time. The nice thing about a library is when you look at the references, if it's a real library run by professional standards, they probably have most of the other references if they're serious ones, and you can go find them somewhere else. If this is in the digital world on the network, what can those clickable references be? I guarantee you they're not IP addresses because they may not exist. The old one, I mean, they're in that. You don't want to go back and change every one of these references every time something moves. You're not going to get them with web addresses because they don't have that long a lifetime. I guarantee you in 100 years, most of those URLs just won't work at all. And in 1,000 years, I dare to say if any of us choose to come back and run the test, they won't work at all. None, not a single one. So that's not a good way to deal with that unless you're willing to take everything you publish and keep re-editing it over time. So what was the solution that seemed to me to be the right one, which is namely, instead of identifying something about the technology of the day, literally identify the data structure. Say, here's the data structure I want, here's its identifier. In 1,000 years, presumably that's still the data structure you want, and however it's managed at that point in time, in whatever technology, you should be able to at least get the object that contains the information. It's a separate question as to whether you can access what's in that object. I'll come back to that too. So open formats are helpful. So if you stored something in, let's say, an Excel proprietary format, then you probably need an Excel program to manifest the data in 1,000 years, which means you need the environment to run it as well. On the other hand, if you had an open format, then other people would know what that is. They could write their own programs to match it. But those formats require the interpreters, and those interpreters have to be managed. So you mainly bought yourself factors of 2, 4, 6, but you haven't bought yourself factors of forever. And so if I were going to come up with a standard for describing a spreadsheet, the way I would do it is to say somewhere in the object that this is of the form matrix, and I assume that's a notion that will carry in the future, and something you could click on would say matrices have the following parameters. They've got rows and they've got columns and ijth entries, and oh, by the way, here are the ijth entries, and so you can then import that into any technology of the future 1,000 years from now that knows how to deal with the displays of the time and the printers of the time and still be able to use it. You don't have to go back to the original program that might have created it. I think this is a very generic area for research because most of the things that we have to deal with don't admit of as simple descriptions as a matrix, which is a very mathematical kind of construct. If you're dealing with other things, it may be harder to do that, but I think it's important that we start. So let me talk about identifiers then, briefly. I assume that they're opaque. That is, if you build in detailed instructions into these identifiers, they're not going to be probably understood in different countries with different languages, and they may not stand the test of time, specifically if those instructions tell you what machines to go to and so forth. So I think they need to be opaque. That is, you got to resolve them to find out what they were intended to convey, and you can resolve them into different descriptions in different languages, and you can even update those descriptions over time, especially as objects move and the like. So you could have pseudorandom strings in your identifiers, date timestamps, alphanumerics, including foreign language strings, and you can have lots of other existing codings now or in the future, ISBNs and so forth. But the management of these identifiers needs to be as decentralized as possible. You cannot expect one company to manage all your identifiers. If you're in the banking business, you're certainly going to want control over that. We certainly know the publishers wanted control over that. We're seeing it in the movie industry and the like. And so you want to be able to do that in a way that lets people take responsibility for their own and yet have the whole system continue to work effectively. So how would this work? So here's a resolution system. You give it an ID, it gives you back state information about the object as defined by the creator. This system, which I show as a box, but I could have showed the internet as a box too. Think of it as a big distributed worldwide system. Thousands, tens of thousands, hundreds of thousands, maybe millions of nodes. It's got to be scalable, it's got to be reliable, it's got to be secure, it's got to be efficient in the fact that you get rapid response, and it must be distributed. Now, distributed comes out of a lot of the other ones, so it's not the primary version, but if you don't have it distributed, you're not going to be able to do it efficiently, you're not going to be able to get backup, you're not going to get data closest to the people who created it and want to use it. But an important part is I'm assuming that the state information of the object is created by the party who created the object in the first place, or their institution. or something, because they're closest to it. They know about it. You might be able to extract some information about it if you stored it somewhere and that place told some other system where it was located. But in general, I would think that state information needs to be defined by the creator, and it needs to be able to be modified securely by that creator. So what are some of the characteristics of this? Well, one, the indirection mechanism must be distributed. It needs local administration of the records. I just said that. It's got to be efficient in terms of giving you the address of a local system to go to, because state information may be in a local machine somewhere in the world, you just don't know where. You've got to get reliability into the system through both backup and mirroring, and as small an amount of central controller administration as is possible to make this system guaranteed to work. So try some examples. So here's a way to organize it. Let's say X is an identifier for a responsible party. It could be Princeton University. And let's say Princeton decides to create an identifier by appending something else to it. They have existing systems they might want to use. They want to create a new one. And so they would create an identifier such as X/Y or maybe X%Y, some way of describing what that is. I'm going to assume the slash for the moment. So if they wanted to then, somebody got an identifier of the form X.Y, they wouldn't know where to go to resolve that, much less to get the information that it's talking about. So it would have to have two steps. One, first it would resolve the X to find the network address where the responsible party keeps the records, and then they would resolve X/Y at that network address. Now you might ask yourself, why not give one long cryptographic string and forget about even identifying the X in there? Because you've got to make sure X is unique to that party. And the reason is if you don't do that, then the only way you're going to be able to resolve this X/Y is by having a giant database of some sort, somewhere that's got everything in the world. It might be 10 to the 30th, 10 to the 40th, 10 to the 50th, and if experience is any guideline, those numbers are probably going to be too small, so suitably far in the future. So this makes it possible to find out who the responsible parties are and then to go to those parties. They may not be willing to give you that information. There may be some restrictions. They may have deleted it, but at least you'll get something back. You might say this information is no longer available or has been retracted, or they may tell you where to go to get it. So this assumes there's some global registry that contains authoritative records for the network addresses of the local services. We can talk more about this. I just want to give you what some of the factors of this. So every value of X then would have to be listed in the global registry. Whereas you might have 10 to the 30th or 10 to the 50th identifiers, you may only have 10 to the 4th or 10 to the 5th or 10 to the 6th organizations or individuals that are crafting these. If it was every individual on the planet, it would be a little bit bigger, but not nearly as big. And so the shorthand terminology we're going to use for X is prefix, for Y is suffix. And let's take a look at how that would work in some detail. So if an organization wanted to authorize multiple individuals to be responsible parties, so let's say 1,000 was Princeton and 1,000.1 could be given to some party that Princeton wanted to manage some set of their records. Or it could be 1,000.cs or 1,000.ee.Kahn. You can create derived prefixes once you have one entry in the system, and these are all guaranteed to be unique. So next question you might ask, what happens if all these records for prefix 1,000 are in the same local service? So suppose Princeton decided they're going to build one big service, even though there are a lot of identifiers they want to give out or a lot of derived prefixes. Do they want to actually have to register all these in the global registry if everyone is going to come back? And the answer is probably not, because what you could do is say, well, that's a special case, and let's just tell anybody who asks, if it starts with 1,000, go to this place, because that's where all the records are. But then you need, as a special case, to deal with the fact that somebody may want to move certain records to someplace else. If it was a publisher, they may want to sell some things, but in general, they may want to move for different reasons. And this is the big question: who administers the system? So remember, I'm talking about trying to avoid as much centralized administration as possible. Here's one way the system could work. There is a central administration. That's where all the primary entry takes place. Under security guidelines. And it's mirrored in a number of places around the world. So somebody who is interested in finding out what an identifier would resolve to would go to any one of these. They could learn about it from the system, and it would come back with the following network address, let's say A.B.C.D, for example. That's not the way you do an internet address, but you get the point. So, but this is a centrally administered system. So I think what we're going to have to move to is a decentralized version where instead of one primary where the administration is, we have multiple primaries that are in fact administered by different parties around the world. So here's administration here, but a different party could administer this system, a different party could administer this system. So if this were, let's say, China, and China was uncomfortable having somebody in the US be in control of all the identifiers, they could have control of it themselves. So then the question is, how do these guys, these primaries, all coordinate with each other? And furthermore, who is in the business of saying who can be a primary and who cannot be a primary? And so I think there needs to be some kind of new nonprofit administration that's overseeing the whole thing that was the one that would be selecting these on some basis. Well, we're assuming here the primaries share a distributed prefix generation scheme, so maybe there are numbers they hand out, like bakery tickets. That could be easily automated with an algorithm. No party gets involved. No duplicates can be allowed, and so you can administer that as well. And every entry has to be signed by the primary that created it. This is all technically doable, but the questions that arise are how you determine who can be a new primary, how can the identity of those primaries be learned reliably, what security mechanisms can be used to protect against unauthorized primaries gaining entry into the system, and how can this new nonprofit administration be guaranteed to remain broadly representative and impartial in its deliberations? This is an issue that is currently being looked at very seriously by many parties in trying to figure out where the internet should go in the future. So I just have a few more slides here, and then I'll take some questions if we still have time. So if you want to access a digital object, the notion it's got to be stored somewhere. So here is a piece of software shown in green that is a digital object management piece of software that knows where your items are stored and knows how to pull them back. And furthermore, the interface to that is all based on the use of identifiers. So you don't have to know file names and you have to know where these are located. You just have to be able to deal with something, and this can be resolved out of the resolution system. And there's got to be metadata associated with everything that's stored there. It could be created by this if it could learn it directly from the objects. But in fact, this is going to be an amalgam of what the creator put in and what could be derived from the object itself. So interoperability, that's the next issue. If this is that software I just showed, and that's a storage system, and here I'm just showing one for simplicity. This could be just a RAID array, it could even be just a local single disk, it could be something across the internet like Amazon S3 or Google or something like that. The combination of the repository interacting with the storage system is called a repository. This green stuff is the digital object management software. If you have one of these around, then the nice thing is if this protocol was derived properly, it can interoperate with any other repository in the globe. So it's a simple form of getting standard interoperability at the level of just getting the objects to be able to move, which is a big issue in its own right. So what might that look like? Here's an example. The parts in red are optional, but it's got at least two identifiers. The first one, shown here, ID 0, would be the identifier for the target operation to apply, and ID 1 would be the actual target for that operation. So if this is get, this might be the command for get is identified this way. It could be the separate object that lays it out as a program. ID 1 might be the identifier of the movie that you wanted to get. You might put parameters in if you wanted to localize it, let's say to the first 2 minutes of the movie rather than the whole movie. Or maybe it's a medical record and you wanted to get a blood pressure portion of it or something else that had a particular type. If you were trying to get something back on a retrieval request, there'd be some output. If you're trying to do a deposit, you might get some input. But in any event, every pair of these can now interface with each other. And this will stand the test of time because you can create any new operations you want by creating new digital objects and just using those identifiers as you see fit. So let's call this the digital object protocol, for lack of a better name. So it will allow you to get the whole object or any part of it. The ability to actually manifest or present the information I consider to be a different kind of function. It's not built into this protocol. Because once you get it back, you're going to have to figure out how do I actually take the information, which might be coded, you might need keys to open it, it might be specific application software, it might be a bitmap that you don't have anything to display at that level of granularity, or it might be not useful, or you may have only descriptions of things that you need to figure out how to present. Now, one of the areas I think we haven't spent nearly enough time on is the area of negotiation in protocols. It really came out first in the speech world, where, you know, if you wanted to kind of talk to somebody in digital form, you sort of wanted to negotiate with them. What do you speak? You speak CVSD, do you speak PCM, can you do 64-bit, or is it LPC10? If it's a document, you may want to know how to get the page image rather than the actual text. And you may want to somehow understand how to use ontologies that are unique to a given field, because that's all you know about in order to actually get the material. So I've just got 2 more slides and then I'm done. The way this protocol would work is you'd establish a connection from, let's say, A to B. It might be a TCP IP connection or whatever the connection protocol is in the future, assuming that's what's used. I'm assuming it's multi-threaded. Optionally, the next step could be to verify the identity of B. I can show you how that can be done implicit here with PKI, because if you're identifying every individual, they're going to have their identifier resolved to their public key, for example, and so you could pass along nonsense strings and ask them to encrypt it. Then, assuming you're comfortable with that, you make a request, again, based on the identifiers as I just showed. Let's say you were asking for a medical record. That repository might want to verify your identity, because this can only be given to a person that's listed in their field by that identity, and they'll either fulfill or deny the request as appropriate. At that point, you can exit the connection or go back and make another request. And it would be closed if nobody else is there. So I guess we're running out of time, but let me just say, by way of concluding remarks, that I believe as we think about systems and what they do and how to design them in the future, some level of abstraction is going to be necessary, especially for long-lived systems. Because I think you have to make the assumption that almost everything is going to change, and you need to think at that level of granularity. You can't assume context when crossing these logical boundaries between one type of system and another, but you've got to be able to convey the important information that the other party will need. Somehow, I think it needs to be through these external systems. I really think interoperability is going to be critical, but it's going to require security for widespread operation, decentralization of administration, and I think it's not only appropriate, but we should go for it to the maximum extent that's practical. Identity management will be needed almost everywhere for individuals, resources, and the information itself, and this can be built into the same system. It doesn't require a separate system to deal with that. And I'm just going to say in passing, even though this looks like everything is identified, anonymity will also be important to make sure we retain in these systems going forward. So I could go into a lot more detail on this, but I think in the interest of time, I probably used up more than I would. If we have time for questions, I'm happy to take them. Thank you very much.
Just a quick question. Who is currently working on this other than yourself actively? Clearly, we need to do it.
Well, I mean, this is an abstraction of, I'm trying to present the general ideas. We have implemented most of the components, made them available open source on the net for people to make use of. The publishing community was first out of the box. Virtually every scientific journal that you get uses some of the identifier technology. They call them DOIs, sort of like took a Boeing jet and put United on the side. So DOIs are like United on the side, but it's our technology. The movie industry is using it to manage their assets. The cable TV industry is using it. Most of the European science groups that deal with big data sets are making use of it to identify the data sets. And we've had a number of discussions with governmental folks in different countries who would like to use it in their countries, but only if they can control the essential administrative aspects of it. So I think it's getting pretty widespread acceptance, but it's something that sort of requires that you kind of roll your own. It's not something you're going to go to, you know, a Microsoft or a Google and find they're going to give you a turnkey solution. We're hoping it influences them in the long term, but right now there's enough capability out there that people can just bring it on themselves and make use of it. In some cases, the results are pretty amazing. Thank you for the question.
Here, and there's also one.
I have two related questions. I can shut. I got a little light. It's Henry Glennie, by the way, Bob. We've met.
Yep.
First is, have you guys considered? I'll give them both at once because they're related. Have you guys considered the possibility of publishing the short organizational tests?
Publishing the what? I didn't.
Publicly available.
I'm sorry, the short what? I didn't hear
The
that.
short prefixes that identify the organizations. You know, the ones that go in your general. The second question is, have you considered the effects of somebody putting an unauthorized address in? So he's asserting, say he comes from Princeton University, doing so when he comes from Stanford and doing it for fraudulent purposes.
Well, first of all, we haven't put out a list of who all of the responsible parties are in our implementation. But on the other hand, everyone is discoverable. So if you got an identifier and it says that's the responsible party's identifier, you can find out who that is. So you can do them one at a time. And you know, I wouldn't be surprised, since we're not clever about it. We're not trying to, you know, it's like 1, 2, 3, 4, 5, 6, 7. So it would be very easy for someone who wanted to do that to pull it down. We just don't do that. On the other hand, you can't put something in that system right now unless an administrator chooses to put it in. And that gets to be a matter of what procedures that they actually use to deal with that. I think if this really does go global with lots of different administrations, you will find people who are more comfortable dealing with certain administrations than others. I'm pretty sure of that. Just like you have in the domain name system today, people who are more comfortable dealing with the more established ones than the brand new ones, they just don't know who they are. There will be misuse, but it won't be in the system. It will simply be that if somebody has an identity in the system, all the system will guarantee is that the person with that identity has the private key that goes along with the stated public key. They can't really change that, you know, without breaking the PKI system. No.
Let's just have one last quick question.
It's on? Okay. So I'm wondering, you've highlighted the engineering challenges, but isn't intellectual property rights, isn't that a much larger problem? Because nowadays companies can't even agree on coming up with a compatible payment system, right? I mean, this is,
So
and this is a much larger scale problem.
Well, I have to say that's where we started, to be quite honest. And the concern, we got involved with the Library of Congress, we got involved with the Copyright Office, actually. And the main concern that we had was people not knowing what they could do with material. If you get something off the internet today, it's not clear what you can do with it. But if you are a party who cares about that from an intellectual property perspective, you can put into the state information that somebody gets out by clicking on the identifiers, not only what are the network addresses where you might go to acquire that information, you can get authentication information for it so you know what you got is right. You can get public keys that are associated with it if that's important. You can get terms and conditions for use. You can get a whole variety of things, including whether there's a charge for it or not from the end party. So the system will support it. But what those policies are and how they're administered by the people that have the intellectual property is a very different matter. In fact, you know what happened with the music industry when they started to make their stuff available. The motion picture industry has been very aware of that and very concerned, and they took steps to try and avoid what happened with Napster happening to them. We see already in the case of people who have other kinds of intellectual property they care about, whether they're chip designs or whatever, trying to figure out how to use this in a way that conveys properly through the resolution system what people can do with it, at the same time secures it through PKI only to people that they want to have access to. So they'll have to have separate agreements with people if they're giving them access to materials that they can further possibly use to limit what they can do under contract.
Okay, thank you, Bob.
Thank you.